lecture, we're going to look at fixed point iterations, or more generally, in the context of nonlinear dynamics, we're going to look at 1D maps. So, what are 1D maps? So, let us go back a step backward and distill the essence of a nonlinear equation. So, in phase space, right, we have an evolution of a trajectory, but through the Poincaré section we have seen that if we have a transect, it could be a time transect because of periodicity, or it could be a space transect as well. You can have a reduced dynamics which you can analyze on a plane, for example, in this case. So we can have a plane like this, so the trajectory can go like this, come back again, intersect over here. So this is 1 2, and it can do this several times. So we are looking at how on this particular plane a point is mapped onto a point, that point is then mapped onto this point, and so on. So such kinds of discrete observations are classified as maps. All right, so we say that x k plus 1 is f of xk, where xk is then mapped to xk plus 1. So in the context of one-dimensional maps, these are just points on a line, and we will look at the evolution of this. And we have seen examples of this when we have analyzed the nonlinear solvers, algebraic solvers, and how it led to oscillations or all these kinds of things. So now we will have a bit more insight, and we will see how a simple map can give rise to seemingly complicated things. So right away we will observe that if we have a fixed point, then x star, if it is the fixed point, is going to be f of x star. So this is by definition a fixed point. The point is mapped onto itself, it's not moving. Okay, so more generally a map can be defined as this. Now let us look at the behavior of a map in the vicinity of a fixed point. So let xk be written in terms of x star plus eta k, where eta k is like the correction to the fixed term. Alright, so we are looking in the neighborhood of a fixed point. So if this is the fixed point, we're looking over here. So now xk plus 1 can be written as x star plus eta k plus 1 is equal to f of x star plus eta k. And we can make use of the Taylor series and write this as f of x star plus f prime x star times eta k plus order eta k squared. Now because x star is a fixed point, x star is going to be equal to f of x, so basically this is becoming f of x star is equal to x star, and so we have this. So this cancels out, and thus we have an evolution of the correction to the fixed point as eta k plus 1 is equal to f prime x star times eta k plus order eta k square. Now if this can be neglected compared to this, then the evolution is quite simple to write, and it is eta k plus 1 is equal to, so f prime at x star we call it as lambda times eta k. Now the eta, rather the eta k will decay if the magnitude of lambda is less than 1. Right, so imagine this is the eta space and this is eta k plus 1. So if magnitude is less than 1, then it will map onto something like this, then it will map onto something like this, then this and this. So each time you are sort of converging towards something. So this is the case where mod lambda, or the magnitude of lambda, is less than 1 and the sign of lambda is positive. If the sign of lambda is negative and the magnitude remains less than 1, then this point will be mapped onto this point over here, which will be then mapped onto this point, then onto this point. So because of the flipping of sign, for each iterate you will have an oscillatory convergence. If lambda is equal to 1, then quite obviously eta k plus 1 will be equal to eta k, and then you have to resort to analyzing the higher orders that you have neglected over here. Okay, so now graphically, how does that particular map, that is x k plus 1 is equal to f of xk, look? Or in fact, what is the solution graphically of this? And we have actually had a look into this. It's not that difficult to recall that on one hand you have x, on the other hand you have f of x. So for example, let this be that particular f of x, and so this is y equal to f of x, and this is x, and this is y, and this function is simply a straight line which goes something like this. It intersects the function over here. So at this particular point we have x is equal to fx, so this line is y equal to x. So at this particular point we have y equal to x, and that is the solution. This is the fixed point. Okay, so this is the fixed point. So now the slope of the function fx at the fixed point governs what the behavior of the convergence will be. If the slope is bounded, that is if the magnitude is less than 1, then we will have convergence. If it is not, then we will diverge. Let us go to the computer and see how this looks like. So let us have a look into the map of let us look at map of x k plus 1 is equal to xk squared. Okay, so let us see how this looks like. So first things first, we'll need an initial value x not equal to say 0.2, or in fact even before starting this, let us first plot these things. So let x equal to n, so we have to first import all the libraries. All right, so we only need this, we don't need solve IBP and mlab over here. All right, so let me run this. Then x will be np dot linspace minus 2 to 2 f equal to x squared and g equal to x. Then we'll do plt dot plot x comma f, x comma g. All right, so this is the fixed point. Okay, obviously x equal to 1 is the fixed point. So now what is the slope at x equal to 1? So the slope at x equal to 1, so this is the function, so it's going to be 2x. At x equal to 1, the slope is greater than 1, it's equal to 2. So we expect that point to be an unstable point. So now let us perform the iterations and actually see whether an initial guess converges to that point or not. So for that, let us in fact reuse this code. So we already have the plot of this. So let x naught be equal to say 0.5. All right, then let us first print out all the values. So for let us do 10 iterations for I in np dot a range 0 to 10. X iterate is equal to x naught squared, and then we will assign x naught as x iterate, and just after this we'll print the value of I, and so the iteration number, and we will print out the value of the present iterate, or x simply. So let it be percentage f, and here we will print I and we will print xi. Alright, so let me run this. So it starts with x equal to 0.25 and then it's converging to 0. It's converging to this root. So obviously this is also a root, and over here the slope is 0 and this attracts. Okay, so immediately we can say that this is a stable root. Let me change the initial condition to 2. Alright, when we start at 2, the iterations are growing out of bound and we have a very large value, and then we have a floating point error. Well, it's a representation error more like it's an overflow error, because it's getting too large for the computer to represent through its the finite byte size that it has. So then we would like to ideally plot what this series of iterations looks like. So before that, let us see per iteration what is really going on. So suppose we have this as x naught. So the first point will be f of, so this particular point is f of x naught. Then we assign it to x1. So this is assigned to this. So this becomes x1. Then this becomes f of x1. This gets assigned to x2 and so on. So let us try to achieve this particular plot on top of this. So per new point we have to plot first this particular line and this particular line. Then so per iterate we have to plot the two sets of lines. One is this and one is this. Alright. So so let me do it over here. So we will first plot plt dot plot. So it will be x naught comma f of x naught. So okay, let me write it like this. We will convert the functions later, and this we have to give a pair of x coordinates. So this also will be this, and this will be 0. Right, then once the new point is found, we will plot, in fact we can do it over here, plt dot plot. The line will be going from x naught comma f of x naught, and this oops, and the second point will be f of x naught, and this will be the same point, so f of x naught. Now the task is to define what f is. So we will go over here, right? We will declare this as a function. So this is the function, and we will define g of x as simply return x. So now this will be f of x and this will be g of x. So let us run this and see what happens. Oops, so I forgot the commas. All right. Okay, that's okay. We need to make lesser number of iterations, or maybe only 4. It's flying away. So let me focus our attention in the vicinity. So I need to change the plot limits. sorry, I need to make it at least 5 so that we can actually see the point. So it's so starting over here, so then it's flying off to infinity. In fact, let me choose 1.2 as the initial point. That will be better for us to visualize. So it's starting over here, then it's going to this, then this point is mapped over here, then to this, and so on. So it eventually flies off to infinity. So because of this slope, every iteration is getting a bump up. So the value of lambda is greater than 1. So after every iteration, eta k plus 1, so if it is equal to lambda times eta k, so this is going to be lambda square times eta k minus 1, and which is going to be lambda cubed times eta k minus 2, and so on. So because of the multiplicity in lambda, if lambda, the magnitude of lambda is greater than 1, then this will fly off to infinity, as we can see over here. Whereas if you take a lower value of the root, it will appear to converge. So if we focus on this particular fixed point, so let me take a guess as minus 0.5, we will see that it converges to the other fixed point. But the other fixed point is not that, I mean, uh, is not that interesting because it's a trivial sort of fixed point. So it's converging like this. Okay, so the the point that I'm trying to make is it depends on what the value of the root is at the point, and depending on that we will achieve convergence or divergence. So let me just fix the plotting so that it doesn't plot every time from the base. So the first point, yeah, so let's just start plotting it like this. All right, so this is how the plot looks like. Let me reduce the scale. Let me make it something like this. So we start off with a guess over here, then it is mapped onto this value, then it is mapped onto this, and this, and then it converges. So it's pretty fast convergence, and the divergence is pretty wild because of the fact that the root is larger than 1. Now let us look at the other case where the root does converge. So let us take a case where xk or xk plus 1 is equal to cos of xk. So let us look at what graphically the root should be. So this is the plot of cos, and this is the straight line. So there is a root somewhere over here. So this is going to be pi by 2. So there's a root between, there's a fixed point between 0 and pi by 2. Alright, so let me copy this snippet. Let me paste it over here, and let me simply make this as np dot cos of x. So let me run this. So okay, let me choose an initial point, something like 0.1. So what is the slope of the root? So that is also critical to see. Well, let us expand the axis a bit. So my bad. This should have been changed, and xi should be f of x naught. It should be simply this. Okay. All right. So we do have convergence happening, and let me increase the number of iterations to highlight how that convergence takes place. So let me take 10 iterations. Boom. So we do have a convergence and it appears to be somewhere around 0.7. So let me reduce the scale to 0.5 to 1.2 so that we have a better look at what is really transpiring. And such kinds of plots are called as cobwebs, and we have already discussed about this. So 0 to 1.2, because they resemble the cobwebs of a spider web, so those are called as cobwebs. All right, so it starts somewhere over here, then it goes on to this, then it maps on to this, and so on. So each iterate, it appears to converge towards this. So at this point, the slope of cosine, you will find that the magnitude is less than 1. So this is how roots can converge depending on the local or the slope at the fixed point. And graphically, it is rather easy to figure out what the fixed point should be. But numerically, for the fixed point, so for the points to converge to the fixed point, you have to ensure that the root is bounded to 1. All right. So now let us proceed to a very famous map, that is xk plus 1 is equal to r times xk times 1 minus xk. So this particular map is also called as the logistic map. So now let us encode this and see what happens. So first of all, I mean, based on the value of r, even before solving this, so let me just encode it. So let me split the cell over here to show you how the plot looks like. So this is how the plot looks like, and there is obviously a fixed point over here and a fixed point at 0. If we increase the value, then let me make it 2. So there's a fixed point over here. So let us focus on 0 to 1, and so what is the maximum going to be? Say at x equal to half, so it's gonna be r by 4. So let us choose this to r by 4 plus 0.1. All right. So this is the fixed point, and now the slope of the fixed point appears to be somewhat close to 0. So we expect this fixed point to be a stable fixed point. It's going to be an attracting fixed point. So let us see. So let me now merge this bit of code along with this, and we will see whether or not that fixed point is indeed attracting or not. Let me remove this. We have to pass r as the additional argument, because in this problem r appears as a parameter to the map, and we'll see that depending on the value of r, we will have varying behaviors. Okay, in fact, let me turn off the printing of the values. If at all you want to play around with this, you can turn on printing the values, and then it will be clearer to you how that iteration actually takes place. But for me, I find it more illuminating. I find it more illuminating if the values are indeed shown through a figure. So this is the guess, then it gets mapped onto this, then it gets mapped onto this, it gets mapped onto this, and so on until it reaches the root. Let us increase the resolution of the curves simply by changing the range. Alright, great. So, and similarly, if we choose a value somewhere over at 0.6, suppose, we should be still getting that kind of a convergence. So there you see it converges. Let me make it 0.8, and again it converges. So regardless of where the initial guess is, you will see that everything converges to the fixed point. Let me increase the value of r. Let me make it 3. Now what happens? Look at this. So when r equal to 3, something quite, I mean, it seems to converge, but it may take a huge amount of iterations to converge. Okay, it's still not converged. Let me take 100 iterations. It's still not converged. So why is this happening? Let us go back and look at the equation. So the f of x that is occurring on the right hand side is equal to rx minus x square. So what is f prime x? Is going to be r minus 2xr. Okay, so so x minus r x times 1 minus x equal to 0. So the solution of this would give you the fixed point, and this is the slope at the fixed point. So we have to substitute the slope over here. So let us expand this. So this is x minus rx plus rx square equal to 0. So we can write it as x square minus x plus x upon r is equal to 0. So this is what x common. So this is x minus 1 plus 1 upon r equal to 0. So x equal to 0 is a root, right? And x equal to 1 minus 1 upon r is a root. So let us superpose that root on top of this. So plt dot plot 1 minus 1 upon r, right? And the 1 minus 1 upon r. Let us mark it with a black marker. So this point is the root. Now we are interested in finding out what the value of this slope is at the root. So the value of this slope will be r times 1 minus twice of 1 minus 1 upon r times, this is the root. So I've just taken r common. This is 1 minus 2x. So what is this? This is going to be r 1 minus 2 plus 2 upon r. So this is going to be 2 minus r. Alright, so when r, so 2 minus r, mod of this less than 1. So if 2 minus r is less than 1, then it means 2 minus r should be less than 1 and it should be greater than minus 1. So the first inequality says that 1 is this, and this implies r should be less than 3, and this, the second inequality, implies that r should be greater than 1. So if r lies in the open set 1 to 3, then we have a stable fixed point. So let me make it 3.1. Let us see what happens. Well, it just keeps on it keeps on going, and most likely it will diverge after so many iterations. I have not kept the number of iterations very high, but let me increase this. Let me make it 4. It will be clear. So at 4, it's going all over the place, and really, I mean, this is something which is quite bizarre to see. You don't expect this kind of behavior from, well, you don't expect, in the sense that for the uninitiated, you will feel that, okay, things will be very well behaved, but it seems to go all over the place. It's not converging to the fixed point. All right, what happens at r equal to 0.5? The same thing. I mean, it goes and it gets attracted towards the other root, that is x equal to 0. Okay, there is no intersection point. So when things are between oops yeah, so when the r is between 1 and 3, we expect the fixed point to be stable like this. But when r exceeds 3, that is when weird things begin to happen. And let us now take a peek into why this kind of behavior actually occurs, so that we can, once we look at the time series, or not the time series but the iterate series, that per iteration how does the root vary, we will be in a position to explain why there is a certain periodicity in the way the roots or the iterates appear. Okay, once that is clear, we can then move on to the bifurcation diagram, where ultimately we will see how that period doubling that we have seen in the case of the van der Pol oscillator, that kind of a period doubling also occurs in such kinds of iterated maps. So let's see. Let us now plot the iterates, how they look like. So let me grab hold of this snippet, and instead of plotting the cobwebs, we are now interested in plotting the, yeah, so we are now interested in plotting the time series, right? So for that we need to plot the following thing. Let me show you. So on the x-axis we'll have the iteration number, and on the y-axis we'll have the actual value of the x, the present x. It will look something like this, or if it converges it will look something like this. So let's have a look. So for that we need to create, so let us create first the n array. So let this be this. So for I in n, right, and we need to store the value of the iterate. So this will be xi is equal to np dot, let me initialize it by zeros, so np dot shape of n. So in case we change n, we already have a soft code method of defining what xi will be, right? So once that happens, we don't need all this plotting anymore, so we can get rid of these lines. We can also get rid of this. All right, and so here I can write xi of I will be xi of I minus 1. Yeah, that's it. That's pretty much the code, and we have to not do this for I equal to 1. For I not equal to 1, we have to do this. All right, so let me run this. So we forgot this. Oops. No, if I not equal to 1. All right, so it runs, and so at the end let us plot. So we will do plt dot plot, and this will be a plot of n versus xi. All right, so well, huh, this has to be 0. Okay, what seems to be the issue? We've not given the initial value. So xi of 0 has to be equal to x naught. Okay, so we've not passed on the initial value and we're trying to iterate. So obviously x equal to 0 was the initial value. And so if I do not write this line, it means that x0 will be 0 because I've initialized everything to 0. It was simply iterating zeros, and 0 is a fixed point. Okay, 0 is a fixed point, so simply we're getting zeros. Okay, so now that we have this in place, we can suppress this and let's see. Okay, so after just a few one iteration, maybe it settles down. Let me change the value of r. Let me make it 2.9. Okay, so it iterates and it converges to 0.65. 0.65 should be equal to the value of 1 minus 1 upon r. So let us also plot that particular point. So plt dot ax h line, and we'll make it pass through 1 minus 1 upon r. So this is that fixed line. This is the root. This is the fixed point that we have calculated analytically. What happens when r exceeds the value of 3? So it appears to oscillate. The values appear to oscillate in a periodic fashion, and the period appears to be 2. Meaning, if I look at this point, after 1, 2, it again repeats. Okay, so let me now increase the value of this to 3.5. Now what happens? It appears to go, so 1, then 2, then 3, then 4, and then again it repeats. So we see that the frequency has increased. All right, and then let me make it 3.9. So now we have this. So there's no discernible. So let me increase the number of iterations to say 400. So there doesn't appear to be a well-defined iteration cycle. And for 3.9, let us see how the cobweb looks like. So we know that something funny happens, but how does it look like? All right, so that is the reason. I mean, it it goes towards the fixed point, then it's repelled away from the fixed point. It keeps on looping all over the place, but it's really never sort of settling down on the actual value, and it appears to be like a limit cycle that we have studied in the nonlinear dynamics part, but there's no periodicity. And let me make it 4.1, let's see, and it blows over to infinity. Well, let me make it 3.95, and we still have something like this. So what's what happens beyond r equal to 3? Okay, there's obviously some period doubling that is happening, and beyond that period doubling, it seems to go off the rails. I mean, there's no discernible pattern that we are able to observe. And let's go back a step and look at how the plot actually looks like. So this was the original plot. Okay, let me suppress the printing of the iterates, and yeah. So if we go back, let me, oops, this has to be there. So this is a different map. In fact, let me take this snippet, let me paste it over here so that we can see the map clearly. So let me remove all these guess values and let me simply plot this. Okay, so this is how the plot looks like. And now beyond r equal to 3, I mean, this is not a stable fixed point. This is an unstable fixed point. It's not converging to that root. But now let me plot instead of fx. We saw that the period doubled. Okay, instead of converging, it took 2 oscillations. So let me plot f of x. Let me plot this. So now we have we saw that it was oscillating between two roots, or not two roots but two iterates, and those iterates were actually this and this. But now we don't know whether these points are stable. We need to guarantee that the slopes of f prime of f of fx, all right? So we're trying to explain why there were two oscillations like this and this were being repeated, meaning it is going to this point, then it is thrown away to this point, then it is again thrown away to this point over all successive iterations. It's not converging. So let me make it 3.1. Okay, so in fact, let me make it 3. Let me show you. So at 3, it is just tangent, and that is the boundary of stability. Below 3, we had the single map, that is f of x, which was converging. So let me also plot x comma f of x comma r. So the green curve intersects the orange curve, and at this parameter at r equal to 3, it was a stable point. But beyond 3, it becomes an unstable point. And beyond 3, after it becomes an unstable point, we see that it oscillates between two iterates. And those two iterates are these roots, this root and this root, while this root becomes unstable. So it is like a bifurcation that occurs where the original root becomes unstable and it goes to two different roots. And you can revisit the earlier lectures on bifurcations to figure out what kind of bifurcation it is. I'm not going to discuss all that over here, but you can imagine that it becomes tangential and now you have two roots appearing, this root and this root. And this root, the slope appears to be low, but at this point also the slope appears to be 0. So these 2 points, these two iterates are stable points, but whether or not the iterates are oscillating around these 2 points remains to be seen. So let us go back to this diagram. Let me copy this. Let me go over here, paste this. Now let me define f of xr as something else. So here we want the double iterate, meaning f of x, okay, because it's going in a 2 cycle, so we want to see the iterate of the iterate because that appears to give us two roots. So let me modify this code so that it returns us the f of x. So let me define this as f1 and let me define f of x comma r, and we will return f1 of x comma r. So it's like calling that function within this function. So let me plot this, and in fact let me plot let me reduce the parameter. After reducing the parameter, let me, well, you can see that it's settling on these two roots. So if I start from here, it's like going in, I mean, in a metaphorical circle, it's going in a rectangle across those two iterates, but let us try to show it also. So if we try to plot the how the iterates occur in the map of f of in the map of in the map of f of x, it appears to converge to this root, but the reality is in the actual map, it's actually going across these 2 points, okay, and that is clear by looking at these oscillations. So now let us increase the value of the parameter. Okay, so now at a certain point it will also become unstable, so probably we have to plot f of this and because we see that the period becomes 4, so we need to plot f of f of f of f of x. Okay, so now it will intersect over here where the slope is mild, so we need obviously more number of points over here. Let me choose this to have 200 points. So it will intersect over here, then over here, so these two become the stable points, but then eventually if you keep changing the parameter you will see more intersection points. And so as you keep changing this, as you keep taking a larger value of r, the stable point will become unstable, it will give rise to more and more points, after which it will descend into chaos, as we have already seen. So when it becomes quite large, so for this also there's a 4 cycle going on. For this, there's something weird going on. There appear to be some intermittent moments. But so how do we quantify all this? I mean, there is something going on. I mean, as we change the parameter r, either it is iterating between, I mean, it goes to a fixed point when the parameter is less than 3. When it is more than 3, it goes into a 2 cycle, then into a 4 cycle, into an 8 cycle, then completely erratic. So how do we make sense of this? And the way is to make a bifurcation map. Okay, so let me first tell you how that map will be generated. So for each value of r, so suppose on the x-axis we have the values of r, and we'll plot, so we'll do say 400 iterations, and we will plot the 200th to 400th iteration, whatever iterates we have, we will plot those values. Okay, so if it goes into a 2 cycle, we'll see 2 points over here. So here is x k going from 200 to 400. So if it settles down to this 2, if it goes flat, then we will see 1 point. If it has something like this, like 1 2 3 4, and then it repeats, so we'll have 1 2 3 4, something like this. So this will call as a bifurcation map. So let us see how we can assess the way this kind of cascading occurs. And once it becomes very erratic, we'll expect to see a lot of points, but will it actually have a cascade or will it not have a cascade? So let's see how to do that. So we'll reuse some of our code as usual. We will take this appears to be a nice snippet to work with. So over here we will increase the iterations to 400, and we will plot not the time series, so plotting n, not the time series but the iteration series. So n versus xi, that will be the iteration series, but we don't want this. In fact, we don't want any of this. So we will plot, so we have to plot r versus xi going from 200 to 400. I mean, by that I mean going to 399. But now r is a scalar value, so we need to have once multiplying this. So when r times once np dot shape xi 200 to 400, or rather let us define this as the y, and okay, so let me, oops, oh sorry. All right, this has to be np dot once. So we have a bunch of, we need to actually only plot the points, we don't need to connect them by a line. Okay, it looks something like this, because it's sort of iterating and getting across all these points one after the other. There is no sequence inherent to this. So now what we need to do is to sweep over the values of R. We need to sweep over all the values of R, and let me change the marker size. Let me make it 1. That looks much better. It looks much more polished. So now let me remove this and let me perform a loop over all the values of R. Okay, so this doesn't change. We initialize it for each set. N doesn't change. Alright, so for R in and p dot linspace, let me just check the parameter value 3.4 to 4. Yeah. Let me take 100 points. So it will do all this plot and it may take a bit of time. So let me run this. Okay, we get this wonderful looking diagram. And what we do see is, okay, let me do it all the way from 2.9 because we want to take R less than 3 as well, because when R is less than 3, we will have only one iterate. So let me run this again. So we have one iterate like this, then it splits into two iterates. It remains like this until 3.4 something. Then it splits again into 4 cycles. Because see, at this transect, at this particular transect, you have 1, 2, 3, 4. So you have the iterations over a large span, sort of going over these 4 points again and again. Okay, so let us see. Let us choose 3.5 just to show what those 4 points are. So it's this point. In fact, let me choose only 50. Okay, so it's this point, then this point, then this point, then this point. So it's 4 distinct points over each cycle over which this set of iterates keep on happening, and that is reflected over in this particular plot. Let us now do this plot, but let me choose a denser sort of let me do it from 3.4. Let me do it from 3.4 to 4, and let me take 200 points. So this may take a while. So this particular diagram is called as the bifurcation map. There are various interesting things to be noted over here. First is there's a period doubling bifurcation that goes on and then it descends into chaos. But in between those doubling cascades, there are windows where it doesn't really sort of double anymore. It goes back to a period 3, in fact. There is only 1, 2, 3, and there's a large window where there are no iterates. It is iterating over this branch, and this branch, and there seems to be a sort of there seem to be these slits where suddenly the bifurcation does not happen anymore, and it goes to a period 3 cycle. Okay, there are a lot of odd things that happen, and I'll give you some links where you can explore all this with the help of some of these tools that we have developed, some of the programs that we've developed. Let me in fact make another diagram but over a different range. I want to show you something interesting. So let me choose it between 3.847 and 3.857. Let me run this. So essentially by dropping the initial ones, we are sort of plotting the long time dynamics. It was we did something like this for the Poincare map as well. And let me show only this lower branch. So let me just change the plt.ylim going from 0.13 to 0.18. So we run it again. It runs rather fast on my PC, but okay, so this is the diagram that we have. And so this diagram that we have plotted for a smaller window than the previous curve, it does appear to be the same kind of diagram that happens over here. So there is a certain self similarity to this entire bifurcation diagram. Once again we see 2, then 4, then 8 descending into chaos, and windows where nothing really goes on, 3 cycles appearing, large gaps where there are no iterates, and so on. So it's quite, unusual, and you would never have predicted that such a simple map, such a logistic map, could give such a rich dynamics. Okay, so you can play around with the parameters, you can see what really happens, you can zoom into the different zones by creating your own um, the small segment where you want to make the plot, to zoom into the appropriate location, and you will keep on seeing this kind of stuff happening. Okay, so this is called as the bifurcation, for the bifurcation diagram for the logistic map. And the such kinds of things do appear for a lot of physical processes as well, such as transition to turbulence and so on, even synchronization of big swarms of things. So it is not just confined to the analysis of a logistic map, but it can extend to a lot of areas of physics and mathematics. And I'll put some links in the description as well. You can have a look and feel free to explore this. And this gives you the platform to perform numerical experiments. So all these things you cannot really go on field and take measurements, but in many cases such kinds of measurements have shown this kind of a bifurcation pattern as well. The most famous experiment is the leaking faucet experiment, and we'll see in the last week whether we can achieve we can record those data and we can construct this diagram also. So with this, I request you to play around, have fun, explore the depths of various maps, and some assignment problems you can really attack them with all your might. And with this, I conclude this particular lecture, and I will see you next time with random numbers. Bye.